How do access points hook up with a wireless LAN controller? Well, that, my friends, is the topic of this nugget. Let's begin. I'd like you to think back to the last time that you watched a movie that you really enjoyed. Maybe it was a streaming movie or at a theater. It doesn't really matter which one it was. But I want you to think about how much effort went into that movie, making it, directing it, making it available, and how easy it was for us to use it. As a customer, all we had to do is sit down, turn it on, or go to the theater, and poof, there's this amazing film for us to watch. We had a very similar experience right here, meaning we configured the controller, we configured the switch, and all we had to do is plug in an access point, and poof, it automatically found the controller and things started working. Behind the scenes, there's a lot of really cool engineering and details that go into making that so easy. And in this nugget, you and I are going to take a look at it because it's important to understand in case something doesn't work correctly. And then it's our job to determine what went wrong and fix the problem. So in our lab, we've got some 1131s here that are plugged in. This is a picture of a model 1260. It's got some extra connectors for additional antennas. But in either case, regardless of which model of access point we're going to use, it's going to need some power for it to boot up. Now, it can get power using power over Ethernet. Maybe you have a power over Ethernet switch that provides that power, or using some type of inline device on the Ethernet cable, or you have an external power connector that plugs in. Regardless of how you want to do it, it needs power so it can boot up. Now, once it powers on and does its power on self-test, one of its first responsibilities as an access point is the process called discovery. Now, what exactly are we trying to discover? We're trying to discover the IP address of a controller so we can connect to that controller. And the four methods we can use for discovery include a broadcast. So, for example, I've got an 1130, a few of them actually, plugged into this network. And what these guys are going to do when they power on is they are going to give a network broadcast asking, hey, are there any wireless controllers within the sound of my voice? And if there are 2 or 3 controllers that are directly connected to VLAN 20 who can respond, they'll respond. Now, in our case here, I don't have any controllers with an IP address on the 20 subnet, so it's not getting any responses from that. But that is one of our several methods for discovering a wireless controller. We also can use flash. These access points all have flash memory, and when they connect once successfully to a wireless LAN controller, they remember it. So the next time they boot up, for example, maybe they're in a different subnet or some other location, they still can remember locally in their flash the IP address of a controller, and they can try to connect to that controller again. Now, of course, if we moved an access point to a different subnet, hopefully there would be DHCP that could hand out an IP address and default gateway. That would make it a lot easier for that access point to actually reach successfully the controller. Another option is to use DHCP. Now, DHCP is really going to give us what? An IP address, a default gateway, maybe a name resolution server. However, we can also hand out options. And one of the options we can hand out is option number 43, which is the IP address of a wireless controller. So if the DHCP service that's running on this VLAN, if it is handing out option 43 and it's handing out the IP address of our wireless LAN controller, which is 10.5, that would be yet another way for an access point to discover a potential wireless controller. Another really interesting option we can use is DNS. So an access point can do the DHCP thing, get an IP address, and then it can make a DNS request looking for this specific name. Cisco CapWap controller. So it'll do a DNS request for that. And if we have a DNS server, and that would very likely be an internal DNS server that has been configured with an IP address associated with that name, the DNS server can answer back, oh, the IP address is 172.16.10.5, or whatever the IP address is of your wireless LAN controller. So these are the 4 methods that we can use for an access point to identify potential wireless controllers that it may want to associate with. I thought it would be really interesting for us to go ahead and capture the data on VLAN 20 to take a look on the Ethernet side at the packets involved in that discovery process. So we're going to use Wireshark as a tool to assist us in looking at the details. If you have interest in Wireshark and setting up captures, hey, come join me over in the Wireshark series. I think you'll love it as well. So let's just do a quick look at what happened. This access point, it booted up, it sent out several CDP messages advertising itself. It did the discover offer request acknowledge. It got its own IP address. It appears it got 20.6 as its IP address. It did a gratuitous ARP, which Cisco devices are prone to do. It then does an ARP for its default gateway of 20.1. It gets an ARP reply back. And check out packet number 12. By the way, this capture I've put up in the Nugget Lab file, so if you want to go through it, you certainly can as well. But this DNS request is looking for a Cisco CapWAP controller right there. And we have a response. Now that just doesn't magically happen, this reply, which is packet 13. I configured DNS to have that host name in it. So the reply came back saying, oh yeah, Cisco CapWAP controller, that's 172.16.10.5. So that part of his discovery was successful. Take a look at what this access point is also doing. It's also in packet number 14, making a request to Cisco LWAP controller. Now, CapWAP is the current method of communicating between the access point and the controller. An older and proprietary system was LWAP. And it appears, based on results, that this access point is doubling down. It's going to try the current protocols and the older protocols. And I did not set up my DNS to respond or to know about the LWAP controller. So the response I got here was, sorry, I got your request, but I just don't know the answer to that second one. So next we have our local network broadcast right here. So here's a broadcast request saying, hey, are there any controllers on this network? And if there were any on that local subnet, they would reply. So this access point is building this list of potential controllers to talk to. It's also doing a discover to a specific 172.16.10.5. Check that out. Now, why is he doing that one? He's doing that discover request because that is in his flash. He has connected successfully in the past to that controller. And as a result, he wants to find out if that controller is still available. And it appears based on that, we're getting a response here as well, indicating that that controller is there. So our access point knows about the controller 3 different ways. Through the DNS request, from the request directly to a controller he's talked to before, both of which were answered positively. And there's also another option here that's kind of hidden, and that is inside of the DHCP. I configured a router to go ahead and answer option 43 with the information regarding our controller. If we take a look at the details of that packet, that's packet number 7. And let me get us a little more real estate here and open up the detail here. If we scroll down, here we have option 43. And let me turn on the bytes view inside of Wireshark. So I'm going to click on view and say I want to see the packet bytes as well. And we'll scroll down to this option 43. And here's the information about that address. So F1 means it's in hex. The 04 represents that there's 4 bytes of data, a 32-bit IP address. And this is the first, second, and third, and fourth octet of the IP address in hex. So AC equals 172.10, again in hex, equals 16. 0A, or just A, equals 10. And 05 in hex is 5. So the address is 172.16.10.5. Now don't shoot the messenger, but when you configure a Cisco router as a DHCP server, you actually need to put in this string in hex to actually communicate that information. And that would be the case for an access point like a 1260. It'd be the case for the 1131, which I'm currently using in the lab, and a whole bunch of others. However, it's not always the case. So you'd want to take a look specifically at your access point to see how it should be represented. Should it be in ASCII or should it be in hexadecimal? In the 1260 and 1131, it needs to be in hex, and it needs to be like this. Let's do a quick road trip over to my router, which is acting as the DHCP server, and I'll show you my config. So this is R1, who's currently trunked into the switched environment and has sub interfaces, one for the 30 subnet. And let's do the show run, and we'll say, please just begin where it says DHCP. And that's perfect. So VLAN 20 is where our access points are all hanging out. And if you'll notice, I provided a network statement, a default gateway form, a DNS server, which is also helpful if they want to resolve that CapWAP wireless controller name. And I also have option 43. And I'm saying hex literally, and then I put F1, which represents hex, the 04 representing there's 4 bytes of data following, and then 172.16.10.5. Also fairly interesting is I have IP host, I have the name of that controller and its IP address right there. I've also enabled DNS server functions on this router. So now when it gets a request for DNS, it replies, and if anybody's asking for that name, that's the answer it's going to give. Now let's suppose that during this discovery phase, we learned about a couple controllers locally, we connected to a controller we connected to last week, we learned about a few others through DHCP and another through DNS. Now we have all these choices. Which one are we going to join? And that boils down to this pecking order right here. And the order is, if we have configured the primary, the secondary, and the tertiary device to connect to, that is the order from the available and discovered controllers that we will connect. Now, by default, there is no primary or secondary and so forth. So what we would need to do when we have a brand new access point that comes up and connects to a controller, we'd want to talk to that access point and tell it specifically, okay, hey friend, guess what? In the future, when you boot up, here's your primary wireless controller. Here's your secondary. Here's your tertiary, so that it knows exactly which one it should go to first based on the ones it found if it's available. To tell an access point which ones are the primary and secondary and so forth, what we do on the controller, once the access point has connected to this controller, simply on the monitor page, scroll down, take a look at your access points, click on detail. It'll show you all the access points that are there. Currently, I just have this one. Click on the access point that you want to configure, and then we're going to go up to high availability. And this, my friend, is where you specify who the primary controller is, who the secondary is, who the third one is, and most importantly, you'd want to include the IP addresses of each. So that based on discovery, if all three of these devices were available and responded to the discovery, the access point would choose the primary one first and it would connect. There's also a failover priority that you can set up for an access point. Let's say, for example, there's a disaster and you lose half of your controllers. Well, based on licensing and capacity, maybe the surviving controllers can't handle all the potential access points. So you can prioritize an access point and give it either a low, medium, high, or critical priority. And then if push comes to shove, like going to a restaurant and there's a celebrity at that restaurant who needs a table, it's very likely that celebrity is going to get the table and you and I are going to have to wait. It works that same way with the access points. An access point who needs to connect to a controller, and if we set it up and have higher priority, the AP with the higher priority is going to get that connection, and somebody else is going to get bumped off that controller. Now let's say that the primary device, secondary, the tertiary device were not available in our discovery. We couldn't reach them, we couldn't access them. The next device that we'd connect to, let's say we had 4 or 5 wireless controllers that responded either because we connected to them in the past or they were sitting on this subnet and heard our broadcast. One of those controllers can be configured as a master. And as a result, if we can't get to our primary, secondary, or tertiary, we will connect to a master if one is configured. Now, by default, no controllers are set up as masters, but it's really easy to set up. It's a single click. Let me show you. In the controller, we were sitting at the details of an access point, looking at the high availability for the primary, secondary, and third controller it should connect with if they're available. To set the controller that we're sitting at up as a master, we'd go up to controller, and then down on the left-hand side, we're going to expand advanced, and there's an option for master controller mode. We're going to select that and simply click the checkbox. We would click on apply to apply that change. So why even do this? We might have a controller in an environment that's just set up for the initial provisioning of access points. So new access points come on the network, they latch onto this controller, and then we use this controller to initially bootstrap or prioritize in the future which wireless controllers an access point should connect to. If there are no controllers that are marked as master, then the least busy device will be connected to. Now, we might ask ourselves, how does an access point know if there's 5 controllers that responded? How does it know which one is the least busy? And the answer is it gives a percentage of utilization. For example, if you have a controller that supports 100 access points and it's got 10, that would be a 10% utilization. If we had another second controller that supported 5,000 access points, and 4,000 were in use, that'd be 80%. It would be more busy. And so the access point, seeing both of their responses in the discover, would go ahead and connect to the one that's least busy at that moment. Now the join process itself is really, really fascinating. We're gonna have 2 channels, 2 logical sessions, if you will, going back and forth between the access point and the controller. We're gonna have one for control, and we're gonna have another one for customer data traffic. And it's interesting that the control traffic is gonna use DTLS, which stands for Datagram Transport Layer Security. Effectively, it's UDP traffic that is running encryption on top of it. to make the conversation private. The destination port for this is going to be 5246. So the access point is going to use some high-numbered source port, but the destination port as it goes to the server is going to be destination port 5246. So the beginning right here of packet 21 is the beginning of our DTLS session, the control channel for CapWAP between the access point and the controller. Right here we can see that it's destined for UDP port 5246. He sourced it from some high-numbered free unused port, and the session begins. We have a little bit of back and forth right here, and then coming from the server is sending to the access point its certificate. So packet 29 is the last packet of the certificate coming to the access point. And then starting in packet number 30, we actually have the access point sending the controller its certificate. So here I'm going to put to wireless LAN controller, and this part is to access point. So they exchange certificates. First, the controller sends his to the access point, and then the access point sends it to the wireless controller in that order. And if we scroll down a little bit more, all this stuff where it says application data, that's all the private stuff because it's encrypted that's now going on between the access point and the controller. So if we grabbed one of these packets, for example, that one right there, we can see that the destination address, the port involved is still 5246. It's encrypted, and both of those factors reinforce that that's the control channel for CapWAP. But now what we're going to discover is that any user traffic, now if a user connects and starts sending data through the network, the CapWAP traffic between the access point and the controller that carries that user traffic is not, by default, that is not encrypted. One of the first things that happens after our join is successful is the controller and the AP are going to have a little heart-to-heart. It goes something like this. Hey, buddy, are you running this version of code? And if the AP says yes, great, we can continue down. However, if the access point says, oh, I'm so sorry, I'm not running that version of code, the controller says, no problem, I've got a copy for you. It downloads it through that control channel to the access point who now has the new code, and he is going to reboot. And he will continue to follow the discovery process, the join process again. This time when he hits the code portion, he's going to say, I've got this version of code. The controller says, that's great. It's exactly what I need you to have. And then it's going to go down to the next step. And that next step is get the config. Get the config required to implement the policy that we've configured on the controller. That's the beauty of having the controller is we specify what the protocols are going to be. For example, we can specify what radios we're going to use. We can specify what type of authentication and authorization we're going to use at the controller, and all that policy and the config that the radio needs, the access point needs to implement that is going to be pushed down at this step right here from the controller to that access point. I mean, how does the access point know it shouldn't turn on its 2.4 gigahertz radios and use it? How does it know that it should use 5 gigahertz? The answer is it's all pushed down from the controller. And again, this is all done on the control channel right here. So once it has the current code, it's got the configuration it needs, it's simply going to run. Also, periodically, there's a little heartbeat that goes on just to make sure that the controller and the access point are happy, they can still talk to each other. So the code, config, and the heartbeat, all of that's done on the control channel between the access point and the controller. So why do we even have these wireless local area networks? It's for the benefit of customers to associate with an access point, join the network, and be able to forward data. The other channel that we're going to have between the access point and the controller is the data channel for CapWAP. And the destination port is 5247. It's also UDP, and by default, it is not encrypted. So let's take a look at a PC. The PC is associated with an access point. We'll just extend them out here. So there's our AP. With its wireless signal, the PC has associated with that access point. It's done DHCP to get an IP address. When it sends a packet, that packet is going to go something like this. Let's say we're pinging off to the internet, some device on the internet. The first frame is going to go from the PC to the access point using whatever wireless technology we have set up, 802.11b or G or A or N. The AP, which is wired to the network, it's part of the distribution system, is going to send that information, that packet, encapsulated in CapWAP on the data channel up to the controller. So it'll have CapWAP headers here. The wireless LAN controller is going to de-encapsulate that, look at it and say, oh, what is it? And make a forwarding decision. So if, for example, the packet's destined out to 8.8.8.8, and let's say it's a ping request, the source MAC address is going to be the PC. The destination MAC address is going to be the PC's default gateway at layer 2, which is that guy right there. So the wireless LAN controller is going to rewrite that, strip off all the CapWAP, rewrite the actual layer 2 frame with the PC's source MAC address, the router's destination MAC address, and then of course at layer 3, we would have this guy's IP address as the source, and whatever the server's destination address is, 8888. And if this router is doing NAT, it's going to be that router's job to change the source IP address from a private address space to a global one before it sends it out. So from PC to AP, from AP to wireless LAN controller, from wireless LAN controller, from a layer 2 perspective to its correct destination as an 802.3 frame. Packet number 217 in the trace in the Nugget Lab files is a great example. So here we have the client, the wireless client, doing a ping request out to 8.8.8.8. As we look at the original IP header, there's the source and there's the destination. And if we open up the details of ICMP, it's going to say it's an ICMP echo request. At layer 2, when that got sent from the Apple device, it looked like this. And we're still on frame 217. The source address is that Apple device. In this case, it was the iPhone. The destination layer 2 address of 89 is the default gateway at 172.16.30.1. The Apple used its own radio to send that. It sent it to the access point, whose MAC address is 9D60, and whose basic service set identifier is also 9D60, same number. So what the access point does with that, it wraps all of that up, encapsulates it using CapWAP, and ships all of it to the controller. So there's the controller as the destination address is the outside header. The source address is the IP address that the AP is currently using. And the contents here and below are going to be delivered to that controller. So the controller receives the CapWAP encapsulated packet, removes the header. It then takes a look at these details and creates a new 802.3 frame as it forwards it with a destination layer 2 address of 89, which is the default gateway, sourcing it from the Apple device. Also, I thought you might be interested in seeing what a trace route looked like from that same device. So here I did a trace route starting in packet 225, and instead of sending 3 packets as a normal trace route would, my iPhone with the little utility it had sent out a single one. So the first one at 225 has a TTL of 1. It got kicked back saying time to live exceeded. Then I sent out with a TTL of 2, and then 3, and then 4, and 5. And that's how we can tell which hops or which routers we're going through to get to a final destination. Again, if you want to spend a lot of time looking at this capture, it's sitting there in the Nugget Lab files ready for you. In this Nugget, we've taken a look at the discovery and selection process. We also leveraged a protocol analyzer to help verify the details of those steps. I hope this has been informative for you, and I'd like to thank you for viewing.